Right now, as you read these words, every atom in your body is vibrating with quantum possibilities. There's a mathematical probability, infinitesimally small but mathematically real, that you could suddenly materialize on the other side of the nearest wall without ever breaking through it. This isn't science fiction. This is quantum tunneling, and it's happening around you every second of every day. Tonight, we're diving deep into one of the most mind-bending phenomena in physics, a quantum effect so strange that it powers the sun, enables our technology, and might even hold the key to the ultimate fate of reality itself. Chapter 1. The Impossible Made Real. Imagine standing in your living room and throwing a baseball at the wall with all your strength. The fastest baseball pitch ever recorded reached over 170 kilometers per hour, a feat that would make any professional pitcher proud. But even that record-breaking fastball would never pass through a solid brick wall. It would bounce off, perhaps leaving a small dent. But the laws of classical physics are absolute in their verdict. Solid objects cannot pass through other solid objects without breaking them apart. Yet, in the quantum realm, this absolute rule becomes merely a suggestion. Subatomic particles routinely perform feats that would make our baseball pitcher weep with envy. They pass through barriers they shouldn't be able to cross, appearing on the other side as if the obstacle never existed. This phenomenon, known as quantum tunneling, represents one of the most profound challenges to our everyday understanding of reality. The story begins in the early 1920s, when physicists were still grappling with the strange new world of quantum mechanics. Classical physics had served humanity well for centuries, providing elegant explanations for everything from planetary motion to the behavior of steam engines. But as scientists peered deeper into the atomic realm, they encountered phenomena that classical physics simply couldn't explain. One of the first hints came from the study of radioactive decay. Scientists observed that alpha particles, essentially helium nuclei, were somehow escaping from the centers of certain atoms, even though they appeared to be trapped by enormous energy barriers. According to classical physics, these particles didn't have nearly enough energy to climb over the barriers that surrounded them. It was like watching a person trapped at the bottom of a deep well, somehow appearing outside without any ladder or rope. The puzzle deepened when researchers began studying the behavior of electrons in metals and semiconductors. They found that electrons could somehow leap across gaps between conductors, even when those gaps should have been completely impassable, according to the laws of classical electricity. The phenomenon occurred so regularly that it couldn't be dismissed as experimental error or some unknown force at work. The breakthrough came when physicists realized that matter itself possesses a dual nature. Particles aren't just tiny billiard balls bouncing around in space. They also behave like waves, with properties that can only be described using mathematical equations that seem to defy common sense. This wave-like nature of matter means that particles don't have precise locations in the way we normally think about objects. Instead, they exist as probability clouds, with varying chances of being found in different locations. Werner Heisenberg's uncertainty principle added another layer to this mystery. It revealed that you cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you try to pin down where a particle is located, the less certain you become about how fast it's moving and in which direction. This isn't a limitation of our measuring instruments. It's a fundamental feature of reality itself. When scientists applied these quantum principles to the problem of particles crossing barriers, They discovered something extraordinary. The wave function that describes a particle's probability of existing in various locations doesn't simply stop at the edge of a barrier. Instead, it extends into and beyond the barrier, albeit with rapidly decreasing intensity. This means there's always a small but finite probability that the particle will be found on the other side of the barrier, even if it doesn't have enough energy to climb over it in the classical sense. The mathematics are both elegant and mind-bending. The probability of tunneling depends on several factors: the mass of the particle, the height and width of the barrier, and the particle's energy. For tiny particles like electrons, tunneling through barriers just a few atoms thick is relatively common. For larger particles like protons, the barriers must be much thinner, or the probabilities become vanishingly small. And for macroscopic objects like baseballs or human beings, the probabilities become so astronomically tiny that they're effectively zero for all practical purposes. This revelation fundamentally changed how physicists understood the nature of reality. The solid, deterministic world of classical physics gave way to a probabilistic universe where outcomes could only be predicted statistically. Particles didn't follow predetermined paths from point A to point B. Instead, they explored all possible paths simultaneously, with some paths being more probable than others. The implications extended far beyond abstract mathematical formulations. Quantum tunneling provided explanations for phenomena that had puzzled scientists for decades. It explained how certain chemical reactions could occur at temperatures far too low for classical theories to predict. It revealed why some materials conduct electricity in unexpected ways. And it opened the door to understanding how the universe itself generates the energy that powers stars and creates the elements essential for life. But perhaps the most profound impact was philosophical. Quantum tunneling forced scientists to confront the uncomfortable reality that the universe operates according to principles that seem to violate our most basic intuitions about how things should work. The boundary between possible and impossible became blurred, replaced by a spectrum of probabilities that extended from the certain to the virtually impossible, but never quite reaching absolute zero. Early pioneers like Niels Bohr, Max Planck, and Albert Einstein spent countless hours debating the meaning of these discoveries. Einstein famously struggled with the probabilistic nature of quantum mechanics, declaring that God does not play dice with the universe. Yet, even Einstein couldn't deny the experimental evidence that continued to mount in favor of quantum tunneling and its associated phenomena. The personal accounts of these early quantum physicists reveal the profound intellectual and emotional challenges they faced. Many described feeling as though they were exploring an alien landscape, where familiar landmarks no longer applied. Some spoke of experiencing what could only be called a form of scientific vertigo, as their fundamental assumptions about reality were systematically dismantled and rebuilt. Max Born, who developed the probabilistic interpretation of quantum mechanics, wrote about the strange mixture of excitement and unease that accompanied these discoveries. The mathematics worked beautifully, providing predictions that matched experimental results with unprecedented accuracy. Yet, the physical picture they painted seemed almost incomprehensible. How could a particle be in multiple places at once? How could it pass through barriers without breaking them? How could the act of observation itself influence the behavior of subatomic systems? These questions launched decades of philosophical debate that continues to this day. But while philosophers argued about the meaning of quantum mechanics, engineers and experimentalists began putting its principles to practical use. They discovered that quantum tunneling wasn't just a curious laboratory phenomenon. It was a fundamental process that could be harnessed for technological applications. The journey from theoretical curiosity to practical application revealed something profound about the nature of scientific discovery. Often, the most abstract and seemingly useless findings in fundamental physics eventually become the foundation for technologies that transform civilization. Quantum tunneling, once considered nothing more than an exotic quantum effect, would eventually enable the development of devices that millions of people use every day. As we stand on the threshold of exploring this quantum landscape, we're reminded that reality is far stranger and more wonderful than our everyday experience suggests. The solid wall next to you, which seems so permanent and impenetrable, is actually a dynamic quantum system where particles are constantly flickering in and out of existence, occasionally performing impossible feats that challenge everything we thought we knew about the nature of matter and energy. The baseball that bounces off the wall follows the predictable laws of classical physics. But zoom in far enough, look closely enough at the quantum dance occurring within every atom of that ball and that wall, and you'll discover a universe operating according to principles so bizarre that they seem more like magic than science. Yet this quantum magic is the foundation upon which all of reality rests, from the fusion reactions in the core of distant stars to the electrical impulses carrying thoughts through your brain at this very moment. Chapter 2. The Mathematics of Impossibility. The mathematics of quantum tunneling reveal a universe operating on principles so strange that even the physicists who discovered them struggled to believe their own equations. When Erwin Schrödinger first wrote down the wave equation that bears his name in 1926, he unleashed a mathematical framework that would fundamentally transform our understanding of reality itself. But hidden within those elegant symbols lay implications so profound that they would challenge everything we thought we knew about the nature of existence. Schrödinger's equation describes how quantum systems evolve over time, treating particles not as discrete objects, but as wave functions that spread throughout space. These wave functions represent the probability of finding a particle at any given location when we actually look for it. The mathematics is deceptively simple in its basic form, yet it captures behavior that seems to violate our most basic intuitions about how the world should work. When applied to a particle approaching a barrier, the Schrödinger equation reveals something extraordinary. The wave function doesn't simply stop at the barrier's edge like a classical particle would. Instead, it penetrates into the barrier itself, decreasing exponentially with distance, but never quite reaching zero. On the far side of the barrier, the wave function emerges again, albeit with greatly reduced amplitude. This mathematical description means there's always a finite probability, however small, that the particle will be found on the other side of the barrier. The probability of quantum tunneling follows a precise mathematical relationship that depends on several key factors. The most important is the exponential decay formula, often written as P equals E to the power of negative 2 times K times L, where P represents the tunneling probability, K is related to the particle's mass and the barrier height, and L represents the barrier width. This exponential dependence means that even small changes in these parameters can lead to enormous differences in tunneling probability. To understand just how dramatic these probability differences can be, let's consider what would happen if you tried to tunnel through a wall. Imagine you're standing in front of a typical brick wall, perhaps 30 centimeters thick. You have a mass of roughly 70 kilograms. and you're moving at a leisurely walking pace of about 1 meter per second. The wall represents an energy barrier of several electron volts due to the electromagnetic forces between atoms. When we plug these numbers into the tunneling probability equation, the result is almost incomprehensibly small. The probability of your successful tunneling would be approximately 10 to the negative power of 10 to the 70th power. To put this number in perspective, if you attempted to tunnel through the wall once every second for the entire age of the universe, roughly 14 billion years, you would still be nowhere close to having a reasonable chance of success. This astronomical improbability exists because quantum tunneling probability depends exponentially on the mass of the object attempting to tunnel. Electrons, with their tiny mass of about 9 times 10 to the negative 31st kilograms, tunnel through barriers with relative ease. Protons, roughly 1,800 times heavier than electrons, find tunneling much more difficult. And macroscopic objects, like human beings, with masses measured in tens of kilograms, face tunneling probabilities so small that they might as well be zero for all practical purposes. The barrier width plays an equally crucial role in determining tunneling probability. Double the thickness of the wall, and the tunneling probability doesn't just halve, it decreases exponentially. This is why quantum tunneling is primarily observed in systems where particles face barriers only a few nanometers thick, roughly the size of several atoms placed side by side. At these microscopic scales, the wave-like nature of matter becomes apparent, and tunneling events occur with measurable frequency. The height of the energy barrier also dramatically affects tunneling probability. Higher barriers correspond to stronger forces trying to keep the particle confined. In the case of nuclear physics, particles must overcome the enormous electromagnetic repulsion between positively charged protons. In electronic systems, electrons must tunnel through the energy gaps that separate different conducting regions. The mathematical relationship remains the same, but the specific values determine whether tunneling occurs frequently enough to observe or remains a purely theoretical possibility. Heisenberg's uncertainty principle adds another layer of complexity to our understanding of quantum tunneling. This fundamental principle of quantum mechanics states that you cannot simultaneously know both the exact position and exact momentum of a particle with perfect precision. The more precisely you try to determine where a particle is located, the less precisely you can know how fast it's moving. This isn't a limitation of our measuring instruments. It's a fundamental feature of quantum reality. The uncertainty principle helps explain how tunneling can occur even when particles don't appear to have enough energy to overcome a barrier. For brief moments, a particle can borrow energy from the quantum vacuum, using this borrowed energy to surmount barriers that would normally be too high. However, this borrowed energy must be repaid quickly within a time interval determined by the uncertainty principle. If the particle can cross the barrier during this brief window, it successfully tunnels to the other side. This energy-time uncertainty relationship means that thinner barriers are easier to tunnel through, not just because the wave function doesn't decay as much, but also because particles can traverse them more quickly. The faster a particle can cross a barrier using borrowed energy, the more likely it is to successfully complete the tunneling process before the quantum debt must be repaid. The mathematical beauty of quantum mechanics becomes apparent when you realize that these seemingly abstract equations make precise predictions about real, measurable phenomena. tunneling currents in electronic devices, the rates of nuclear decay, and the efficiency of certain chemical reactions can all be calculated with remarkable accuracy using these quantum mechanical formulations. The mathematics doesn't just describe what we observe, it predicts phenomena that scientists hadn't even thought to look for. Consider the probability cloud that represents a particle's possible locations. In classical physics, a particle has a definite position and follows a specific trajectory from one point to another. In quantum mechanics, the particle exists as a spread-out wave of possibility until the moment we actually measure its location. This probability cloud can extend beyond classical boundaries, penetrating into regions that should be forbidden according to our everyday experience. The wave function that describes this probability cloud has a peculiar mathematical property. It can have non-zero values even in regions where the particle doesn't have enough energy to exist, according to classical physics. Inside a barrier, the wave function becomes what mathematicians call evanescent. It decays exponentially with distance, but maintains a finite amplitude. This evanescent wave carries no net flow of energy or momentum, yet it provides the mathematical pathway through which tunneling can occur. When the barrier ends, the evanescent wave can couple back into a propagating wave on the far side. The strength of this coupling determines the tunneling probability. For thin barriers, a significant fraction of the wave amplitude can emerge on the other side. For thick barriers, the exponential decay reduces the amplitude to virtually nothing by the time the wave reaches the far edge. The quantum mechanical calculation of tunneling probability requires solving the Schrödinger equation for the specific geometry and energy landscape involved. For simple, rectangular barriers, this calculation yields analytical solutions that clearly show the exponential dependence on barrier parameters. For more complex barrier shapes, numerical methods must be used, but the fundamental physics remains the same. One of the most remarkable aspects of these calculations is their predictive power. Scientists can design experiments to test quantum tunneling predictions with extraordinary precision. In scanning tunneling microscopes, for example, the tunneling current between a sharp metal tip and a surface varies exponentially with the distance between them, exactly as predicted by quantum mechanics. These devices can detect changes in separation as small as a fraction of an atomic diameter, all based on the mathematical description of electron tunneling. The mathematical framework also reveals why quantum effects become less noticeable as objects become larger. The de Broglie wavelength, which characterizes the wave-like properties of matter, becomes smaller as mass increases. For electrons, this wavelength is comparable to the size of atoms, making wave-like behavior easily observable. For baseball-sized objects, the de Broglie wavelength becomes smaller than the diameter of a proton, making quantum effects virtually undetectable. This mathematical relationship explains why we don't observe quantum tunneling in our everyday experience. The probability calculations that yield finite results for subatomic particles produce numbers so small for macroscopic objects that they become physically meaningless. You could wait for time periods far exceeding the age of the universe and still never observe a person tunneling through a wall, despite the mathematical probability being technically non-zero. Yet, the same mathematical formalism that makes human tunneling impossibly unlikely also explains how the universe generates the energy that powers stars and creates the elements essential for life. The nuclear fusion reactions in stellar cores depend critically on quantum tunneling to overcome the electromagnetic barriers that keep atomic nuclei apart. Without this quantum effect, the mathematical models predict that stars would be cold, dark objects, incapable of sustaining the nuclear fires that illuminate the cosmos. The probability calculations become even more fascinating when applied to systems with multiple particles. While the chance of a single proton tunneling through the Coulomb barrier in a star is extraordinarily small, stars contain vast numbers of protons in their cores. When you multiply the small individual probability by the enormous number of attempts occurring every second, the result is a measurable and sustained rate of nuclear fusion. This interplay between individual quantum probabilities and large-scale statistical effects reveals one of the most profound insights of quantum mechanics. Individual quantum events are fundamentally unpredictable, governed only by probability. Yet when large numbers of quantum systems are involved, these random individual events combine to produce remarkably predictable average behaviors. The mathematics of quantum tunneling thus bridges the gap between the uncertain quantum world and the apparently deterministic classical world we experience daily. The exponential nature of tunneling probability also means that quantum effects can be incredibly sensitive to environmental conditions. Small changes in temperature, pressure, or electromagnetic fields can dramatically alter tunneling rates. This sensitivity makes quantum tunneling both a powerful tool for probing the properties of materials and a significant challenge for engineering quantum devices that must operate reliably under varying conditions. As we contemplate these mathematical relationships, we're confronted with a universe far more subtle and interconnected than our intuitions suggest. The same equations that make human wall tunneling impossible also make stellar fusion possible, demonstrating how quantum mechanics simultaneously constrains and enables the phenomena we observe around us. The mathematics doesn't just describe reality. It reveals the hidden quantum foundations upon which all classical behavior ultimately rests. Chapter 3. When the Sun Learned to Shine. In the early decades of the 20th century, astrophysicists faced a puzzle that threatened to unravel everything they thought they understood about the cosmos. The sun was shining, bathing Earth in life-giving energy. Yet, according to the best calculations available at the time, it shouldn't have been able to sustain nuclear fusion at all. The temperatures and pressures in the solar core, while enormous by terrestrial standards, fell far short of what classical physics demanded for hydrogen nuclei to overcome their mutual electromagnetic repulsion and fuse together. This stellar paradox emerged from careful measurements of the sun's core temperature, estimated at approximately 15 million Kelvin. While this temperature seems almost incomprehensibly hot, it corresponds to an average particle energy of only about 1 kiloelectron-volt. Meanwhile, the electromagnetic barrier that keeps protons apart, known as the Coulomb barrier, stands at roughly 1 million electron-volts for the fusion of 2 hydrogen nuclei. The mathematical disparity was stark and troubling. Particles in the solar core possessed barely 1,000th of the energy they needed to overcome the forces keeping them separated. Classical physics painted a grim picture of stellar evolution. If nuclear fusion required particles to possess enough kinetic energy to surmount the Coulomb barrier through brute force alone, then stars would need core temperatures exceeding 100 billion Kelvin to sustain fusion reactions. At such temperatures, no star could exist in any recognizable form. The electromagnetic and thermal pressures would instantly tear apart any gravitationally bound object, dispersing its material across vast regions of space. The implications of this classical calculation extended far beyond stellar physics. Without sustained nuclear fusion, stars would be nothing more than slowly cooling balls of gas, gradually radiating away their gravitational potential energy over periods of millions of years. The universe would be a cold, dark place, populated by dim, dying objects, incapable of generating the energy necessary to drive chemical evolution or support the complex processes that give rise to life. Early astrophysicists like Arthur Eddington recognized the profound nature of this dilemma. In his 1920 paper, The Internal Constitution of the Stars, Eddington speculated that some unknown mechanism must enable stellar fusion at temperatures far below the classical threshold. He correctly intuited that the conversion of hydrogen into helium could provide the enormous energy output observed from the Sun, but the physical process remained mysterious. The solution emerged from the developing field of quantum mechanics, though it took several years for physicists to recognize its application to stellar physics. The key insight came from understanding that particles don't need to possess enough energy to climb over barriers. They can tunnel through them instead. This quantum mechanical process allows nuclear fusion to occur at temperatures where classical physics would forbid it entirely. Quantum tunneling transforms the nuclear fusion probability from zero to finite, though still extraordinarily small for any individual encounter between two protons. The probability follows the familiar exponential dependence on barrier parameters, with the massive electromagnetic repulsion between protons, creating an enormous energy barrier that severely suppresses tunneling rates. For two protons approaching each other in the solar core, the probability of successful fusion in any given collision is roughly 1 in 10 trillion. This probability might seem discouragingly small, but stellar cores contain staggering numbers of protons. The Sun's core holds approximately 10 to the 56th power hydrogen nuclei, all in constant thermal motion at temperatures of 15 million Kelvin. These particles collide with each other billions of times per second, creating an astronomical number of opportunities for the rare tunneling events that enable fusion. The mathematical framework for stellar fusion involves what physicists call the Gamow peak, named after George Gamow, who first applied quantum tunneling theory to nuclear processes in 1928. The Gamow peak represents the optimal balance between two competing factors: the exponentially decreasing tunneling probability as particle energy decreases, and the exponentially decreasing number of high-energy particles as described by the Maxwell-Boltzmann distribution of thermal energies. Most fusion events occur among particles with energies well below the classical threshold for overcoming the Coulomb barrier. These particles succeed through quantum tunneling, borrowing energy from the vacuum for brief moments to penetrate the electromagnetic barrier separating atomic nuclei. The borrowed energy must be repaid quickly, within time intervals determined by Heisenberg's uncertainty principle. But this proves sufficient for protons to approach close enough for the strong nuclear force to bind them together. The proton-proton chain reaction that powers the Sun begins when two hydrogen nuclei tunnel through their mutual Coulomb barrier to form a deuteron. This initial step is the bottleneck that determines the overall fusion rate in stars like our Sun. One of the protons must simultaneously convert to a neutron through beta plus decay, a process that involves the weak nuclear force and occurs with extremely low probability. The combination of tunneling through the Coulomb barrier and the rare weak interaction makes the first step of stellar hydrogen fusion extraordinarily unlikely for any individual pair of protons. Yet, this inefficiency proves crucial for stellar longevity. If fusion occurred more readily, stars would burn through their hydrogen fuel in millions rather than billions of years. The quantum mechanical suppression of fusion rates allows stars to maintain steady energy output over timescales long enough for planets to form and complex chemistry to evolve. Without quantum tunneling setting the precise rate of stellar fusion, the universe would be populated either by stars that burn out too quickly to support planetary evolution or by objects too cool to drive the nuclear processes that create heavy elements. The temperature dependence of tunneling-enhanced fusion rates explains many observed features of stellar evolution. Hotter, more massive stars have higher core temperatures that increase tunneling probabilities, leading to faster fusion rates and shorter lifetimes. Cooler, less massive stars like red dwarfs operate with fusion rates so slow that they can continue burning hydrogen for trillions of years, far longer than the current age of the universe. Quantum tunneling also enables the formation of elements heavier than hydrogen and helium through processes that classical physics would render impossible. The triple alpha process, which creates carbon by fusing 3 helium nuclei simultaneously, requires quantum tunneling to overcome multiple Coulomb barriers. Without this process, the universe would contain only the lightest elements created during Big Bang nucleosynthesis, and the complex chemistry necessary for life could never emerge. The carbon-nitrogen-oxygen cycle, which dominates energy production in stars more massive than our Sun, similarly depends on quantum tunneling to drive fusion reactions involving nuclei with higher electric charges and correspondingly stronger electromagnetic barriers. Each step in these reaction chains requires particles to tunnel through increasingly formidable Coulomb barriers, yet the exponential sensitivity of tunneling rates to temperature allows these processes to become efficient in the cores of massive stars. Silicon burning, which occurs in the final stages of stellar evolution before core collapse, pushes quantum tunneling to its limits. The enormous Coulomb barriers surrounding silicon and other heavy nuclei require extreme conditions to permit fusion, yet tunneling enables these reactions to proceed at temperatures around 3 billion Kelvin. These processes synthesize iron peak elements through complex networks of fusion and photodisintegration reactions, all mediated by quantum tunneling effects. The role of quantum tunneling in stellar nucleosynthesis extends beyond individual fusion reactions to influence the overall structure and evolution of stars. The steep temperature dependence of tunneling-enhanced fusion rates creates strong negative feedback that helps stabilize stellar cores. If a region becomes slightly hotter than its surroundings, the fusion rate increases dramatically, generating additional pressure that causes the region to expand and cool. This self-regulating mechanism prevents stellar cores from developing the runaway temperature increases that would lead to catastrophic instability. Understanding quantum tunneling in stellar contexts also resolved long-standing puzzles about the observed abundances of elements in the universe. The relative concentrations of different isotopes produced by stellar nucleosynthesis depend sensitively on the quantum mechanical tunneling rates that govern various nuclear reactions. Detailed calculations of these rates, combined with models of stellar structure and evolution, successfully explain the observed cosmic abundances of elements from carbon to iron. Neutron star formation during supernova explosions provides another dramatic example of quantum tunneling's cosmic significance. When stellar cores collapse under their own gravity, the extreme conditions enable rapid neutron capture processes that synthesize the heaviest elements in the periodic table. These processes require quantum tunneling to overcome Coulomb barriers even more formidable than those encountered during normal stellar burning. Yet they occur on timescales of seconds rather than millions of years. The quantum mechanical nature of stellar fusion also influences our understanding of stellar lifetimes and the ultimate fate of the universe. As stars exhaust their nuclear fuel, they evolve through sequences of burning phases, each involving progressively heavier elements and requiring higher temperatures to achieve significant tunneling rates. The final stages of stellar evolution, including white dwarf formation and neutron star creation, depend critically on quantum mechanical processes that classical physics cannot adequately describe. Binary star systems reveal additional complexities in quantum tunneling-driven fusion. When matter from one star accretes onto a white dwarf companion, the accumulating material can undergo explosive nuclear burning through tunneling-enhanced fusion reactions. These thermonuclear explosions, observed as novae and type Ia supernovae, provide important astronomical distance indicators and contribute to the cosmic abundance of intermediate mass elements. Modern observations of stellar oscillations and neutrino fluxes from the solar core provide direct confirmation of the quantum mechanical models of stellar fusion. The neutrinos produced by fusion reactions in the Sun's center carry information about the nuclear processes occurring deep within the star, allowing scientists to test their understanding of quantum tunneling rates under extreme conditions. These measurements confirm that stellar fusion proceeds exactly as predicted by quantum mechanical calculations, validating our understanding of tunneling effects in cosmic context. The profound realization that quantum tunneling enables stellar fusion illuminates the deep interconnection between microscopic quantum effects and cosmic scale phenomena. The same mathematical principles that govern electron tunneling in laboratory devices also determine whether stars can shine and whether the universe can evolve the chemical complexity necessary for life. Without quantum tunneling, the cosmos would be a vastly different and far more desolate place, populated by cold stellar remnants, in a universe forever locked in chemical simplicity. Chapter 4. The Technology Revolution, Hidden in Plain Sight. The device in your pocket that you check dozens of times each day operates on principles that would have seemed like pure magic to scientists just a century ago. Your smartphone, tablet, or laptop contains billions of transistors, each one exploiting quantum tunneling to store and process information in ways that classical physics declared impossible. Every time you save a photo, send a message, or stream a video, you're witnessing quantum mechanical phenomena that occur trillions of times per second within the silicon circuits that power our digital civilization. Flash memory, the technology that stores data in virtually every electronic device you own, represents one of the most elegant applications of controlled quantum tunneling ever developed. Inside each memory cell, electrons must tunnel through an insulating barrier to reach a floating gate where they become trapped, representing stored information. This process requires precisely controlling quantum tunneling rates to ensure data can be written reliably while remaining stable for years without external power. The physics behind flash memory involves what engineers call a floating gate transistor, a structure that would be impossible to understand without quantum mechanics. The floating gate sits embedded within an insulating layer, completely surrounded by material that classical physics says electrons cannot penetrate. Yet, when the right voltage is applied, electrons tunnel through this insulating barrier with clockwork precision, accumulating on the floating gate and changing the electrical properties of the transistor in measurable ways. Writing data to flash memory requires ramping up the voltage across the insulating layer until quantum tunneling becomes probable enough for electrons to cross the barrier in reasonable time. The exponential dependence of tunneling probability on voltage means that small changes in applied electric field can dramatically alter the rate at which electrons tunnel onto the floating gate. Engineers have learned to exploit this sensitivity to create memory devices that can be programmed quickly while maintaining excellent data retention over decades. Erasing stored data reverses the process, applying voltages that encourage electrons to tunnel back off the floating gate. The asymmetry between writing and erasing operations reflects the different barrier heights that electrons encounter when tunneling in opposite directions. This quantum mechanical asymmetry allows flash memory to maintain data integrity even when subjected to electrical noise and temperature fluctuations that might otherwise corrupt stored information. The scanning, tunneling microscope represents perhaps the most dramatic demonstration of quantum tunneling's technological potential. Invented by Gerd Binnig and Heinrich Rohrer at IBM Zurich in 1981, this remarkable instrument earned its creators the Nobel Prize in Physics just 5 years later. The microscope works by bringing an atomically sharp metal tip within a few angstroms of a conducting surface and measuring the quantum tunneling current that flows between them. The exponential dependence of tunneling current on distance makes the scanning tunneling microscope extraordinarily sensitive to surface topography. Moving the tip just 1 angstrom closer to the surface can increase the tunneling current by an order of magnitude. This sensitivity allows the microscope to resolve individual atoms on surfaces, creating images with detail that surpasses even the most powerful optical microscopes by factors of millions. Operating a scanning tunneling microscope requires maintaining the tip surface separation with precision that challenges the limits of mechanical engineering. Thermal vibrations, acoustic noise, and electromagnetic interference can all disrupt the delicate tunneling junction. The most sophisticated instruments operate in ultra-high vacuum chambers, cooled to near absolute zero, suspended on elaborate vibration isolation systems that filter out disturbances down to frequencies below 1 Hz. The tunneling current in these microscopes typically measures just a few picoamperes, requiring amplification systems capable of detecting individual electrons crossing the junction. The mathematics that govern this current flow derive directly from the quantum mechanical tunneling probability calculations we explored earlier. The current depends exponentially on the tip surface separation, the local density of electronic states in both the tip and sample, and the applied voltage between them. Beyond simply imaging surfaces, scanning tunneling microscopes can manipulate individual atoms with extraordinary precision. Scientists have used these instruments to spell out company logos in xenon atoms, create artificial molecules by positioning atoms in specific arrangements, and study how individual atomic defects influence the electronic properties of materials. Each of these manipulations relies on the same quantum tunneling effects that enable the microscope's imaging capabilities. The technological applications of controlled quantum tunneling extend far beyond memory devices and microscopes into the fundamental operation of modern electronics. Tunnel diodes, first developed by Leo Esaki in 1957, exploit the peculiar voltage dependence of quantum tunneling to create components with negative resistance characteristics impossible to achieve with classical electronic devices. In tunnel diodes, electrons tunnel through barriers formed at interfaces between specially prepared semiconductor materials. The tunneling probability depends sensitively on the energy alignment between electronic states on either side of the barrier. By applying external voltages that modify this energy alignment, engineers can create devices where increasing voltage actually decreases current flow, producing the negative resistance effect that makes tunnel diodes useful as amplifiers and oscillators in high-frequency applications. Josephson junctions, which consist of two superconductors separated by a thin insulating barrier, represent another quantum tunneling technology with revolutionary applications. Cooper pairs. The bound electron pairs responsible for superconductivity can tunnel through barriers that would completely block individual electrons. This tunneling of Cooper pairs creates the Josephson effect, enabling the development of superconducting quantum interference devices that can measure magnetic fields with sensitivity, approaching the fundamental limits imposed by quantum mechanics. Modern quantum computers rely heavily on controlled quantum tunneling to create and manipulate the quantum states that store and process information. Superconducting qubits, one of the leading platforms for quantum computation, use Josephson junctions to create artificial atoms with precisely controllable energy levels. Quantum information is encoded in the tunneling of Cooper pairs between different superconducting islands, creating superposition states that can exist simultaneously in multiple configurations. The challenge of unwanted quantum tunneling has become a major concern in the development of ever smaller electronic devices. As transistors shrink toward atomic dimensions, electrons begin to tunnel through barriers that were designed to confine them completely. This quantum mechanical leakage creates power consumption problems and limits the ultimate scaling of classical computing technology. Gate tunneling in modern field effect transistors occurs when the insulating layers become so thin that electrons can tunnel directly from the conducting channel to the gate electrode. This parasitic current wastes power and degrades device performance, forcing engineers to develop new materials and device architectures that maintain quantum mechanical isolation while preserving the electrical control necessary for transistor operation. The transition from beneficial to problematic quantum tunneling illustrates the double-edged nature of quantum mechanical effects in technology. The same physical principles that enable flash memory and scanning tunneling microscopes also impose fundamental limits on how small conventional electronics can become. Engineers must now think quantum mechanically when designing devices, carefully balancing the exploitation of quantum effects against their potentially disruptive consequences. Quantum tunneling also plays crucial roles in the operation of solar cells, light-emitting diodes, and laser diodes. In these optoelectronic devices, charge carriers must tunnel through barrier regions to reach active layers where light emission or absorption occurs. The efficiency of these devices depends critically on engineering the barrier heights and widths to optimize tunneling rates for specific operating conditions. Tunnel field effect transistors represent an emerging technology that deliberately exploits quantum tunneling as the primary switching mechanism. Unlike conventional transistors that rely on thermal emission of charge carriers over energy barriers, tunnel transistors use electric fields to modulate quantum tunneling rates through barriers. This approach potentially enables lower power operation and steeper switching characteristics than conventional devices. The development of molecular electronics pushes quantum tunneling applications to even smaller scales. Individual molecules can serve as tunneling barriers or active device elements, with their electronic properties determined by quantum mechanical calculations of molecular orbital structures. Single-molecule devices might eventually enable computing systems with component densities impossible to achieve with conventional semiconductor technology. atomic force microscopes, close relatives of scanning tunneling microscopes, use quantum mechanical effects to measure forces between atomically sharp tips and sample surfaces. While these instruments don't rely directly on tunneling currents, they exploit quantum mechanical interactions between atoms at the tip apex and surface atoms to achieve extraordinary spatial resolution in force measurements. The practical implementation of quantum tunneling devices requires sophisticated understanding of materials science, surface physics, and nanofabrication techniques. Creating reliable tunneling barriers demands atomic-level control over material, composition, and structure. Even single atomic defects can dramatically alter tunneling characteristics, making quality control a quantum mechanical challenge. Environmental factors like temperature, humidity, and electromagnetic fields can significantly influence quantum tunneling rates in practical devices. Engineers must account for these variations when designing circuits that maintain reliable operation across wide ranges of operating conditions. The exponential sensitivity of tunneling to barrier parameters makes these devices both remarkably sensitive scientific instruments and challenging components for robust technological applications. Looking toward future applications, quantum tunneling may enable entirely new categories of electronic devices. Proposals for tunneling-based memory with switching speeds approaching femtoseconds could revolutionize high-speed computing applications. Three-dimensional integration of tunneling devices might overcome the scaling limitations that threaten to end Moore's law in conventional semiconductor technology. The convergence of quantum tunneling with other quantum mechanical phenomena opens possibilities for hybrid devices that exploit multiple quantum effects simultaneously. Spin-polarized tunneling combines quantum tunneling with magnetic effects to create devices for quantum spintronics applications. Tunneling combined with quantum interference effects enables new types of electronic devices with properties that have no classical analogs. As we surround ourselves with devices that operate through quantum tunneling, we're reminded that the boundary between the exotic quantum world and everyday technology has largely disappeared. The same mathematical principles that make human wall tunneling impossible also enable the electronic civilization that defines modern life. Every quantum tunneling event in your devices represents a small victory of human ingenuity over the apparent limitations imposed by classical physics, demonstrating how deep understanding of fundamental science ultimately transforms the technological landscape in ways that would have seemed miraculous to previous generations. Chapter 5. The Deepest Mysteries of Quantum Reality. The deepest mysteries of quantum reality emerge when we confront the profound puzzle of measurement itself. Every time a scientist observes a quantum system, something extraordinary happens that challenges our most fundamental assumptions about the nature of reality. The act of measurement appears to transform a quantum system from existing in multiple states simultaneously into having definite classical properties. This transformation, known as wave-function collapse, represents one of the most enigmatic aspects of quantum mechanics and lies at the heart of ongoing debates about what quantum tunneling truly means for our understanding of existence. When an electron approaches a barrier in a quantum tunneling experiment, the mathematics of quantum mechanics describes it as existing in a superposition of states. The electron simultaneously explores all possible paths through the experimental apparatus, including trajectories that pass through the barrier and others that reflect back from it. This superposition isn't merely a limitation of our knowledge about the electron's behavior. It represents the actual physical state of the system before measurement occurs. The wave function that describes this superposition contains information about all possible outcomes of the tunneling experiment and their relative probabilities. In the mathematical formalism, the electron doesn't have a definite location or momentum until the moment we perform a measurement to determine whether it successfully tunneled through the barrier. Before measurement, the electron exists in what physicists call a coherent superposition, where quantum interference effects can occur between different possible paths. Yet the moment we place a detector on one side of the barrier to check whether the electron has tunneled through, something dramatic happens. The wave function appears to collapse instantaneously, and the electron suddenly acquires definite properties consistent with either having tunneled or having been reflected. This collapse occurs faster than light could travel between different parts of the experimental apparatus, suggesting that quantum measurement involves non-local effects that transcend our ordinary concepts of space and time. The measurement problem becomes even more perplexing when we consider what constitutes a measurement in the first place. Must a conscious observer be present for wave function collapse to occur? Does the presence of any measuring device trigger the collapse, regardless of whether anyone looks at the results? These questions have puzzled physicists for nearly a century and continue to generate heated debates about the fundamental nature of quantum reality. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in determining physical reality. In this view, the universe exists in superposition until conscious observers make measurements that collapse wave functions into definite outcomes. This perspective implies that reality itself might be participatory, with conscious beings serving as co-creators of the physical world through their observations and measurements. The many-worlds interpretation offers a radically different perspective on quantum measurement and tunneling. According to this view, wave function collapse never actually occurs. Instead, every quantum measurement causes the universe to split into multiple branches, each corresponding to a different possible outcome. In the context of quantum tunneling, this means that both outcomes, tunneling and reflection, actually happen, but in separate branches of reality that can no longer communicate with each other. From the many worlds perspective, when an electron encounters a barrier, the universe splits into at least two branches, one where the electron tunnels through, and another where it reflects back. Conscious observers also split along with the branching universe, so each version of the observer experiences only one outcome, while remaining unaware of the other branches where different results occurred. This interpretation preserves the deterministic evolution of the universal wave function, while explaining why individual observers experience apparently random quantum outcomes. The implications of many worlds for our understanding of quantum tunneling are staggering. Every quantum tunneling event that occurs anywhere in the universe causes reality to branch into multiple versions, creating an ever-expanding multiverse of staggering complexity. The tunneling reactions in stellar cores that power the Sun create billions of branches every second, each representing a slightly different history of nuclear fusion rates and stellar evolution. Quantum entanglement adds another layer of mystery to the relationship between tunneling and measurement. When particles become entangled, measuring the quantum state of one particle instantly affects the properties of its partner, regardless of the distance separating them. This non-local connection appears to operate faster than light, challenging our concepts of causality and locality that form the foundation of classical physics. In quantum tunneling experiments involving entangled particles, measurement of one particle's tunneling behavior can instantaneously influence the quantum state of its entangled partner. This suggests that quantum tunneling events might be connected across vast distances through entanglement networks that transcend ordinary space and time. Some theorists propose that the entire universe might be connected through a web of quantum entanglements that originated during the Big Bang. The information paradox in quantum tunneling raises profound questions about the preservation of information during quantum processes. When a particle tunnels through a barrier, does all the information about its initial state transfer to the final state, or does some information get lost during the tunneling process? This question becomes particularly acute when considering black holes, where quantum tunneling processes might allow information to escape from regions where classical physics says nothing can emerge. Quantum tunneling challenges our classical concepts of locality and causality in fundamental ways. The tunneling process appears to occur instantaneously, with particles seeming to cross barriers without spending any time in transit. This zero transit time paradox suggests that tunneling might involve non-local quantum correlations that connect the initial and final states without requiring the particle to follow a continuous path through the intervening space. The role of decoherence in quantum tunneling provides insights into how classical behavior emerges from quantum foundations. When quantum systems interact with their environment, they lose the coherence necessary to maintain superposition states. In tunneling experiments, environmental decoherence can destroy the quantum interference effects that enable tunneling, effectively suppressing quantum behavior and restoring classical physics. Understanding decoherence helps explain why we don't observe macroscopic quantum tunneling in everyday life. Large objects interact so strongly with their environment that their quantum coherence disappears almost instantly, preventing the superposition states necessary for tunneling from surviving long enough to be observed. This decoherence process creates an effective boundary between the quantum and classical worlds. The philosophical implications of quantum indeterminacy extend far beyond physics into questions about free will, causality, and the nature of reality itself. If quantum tunneling events are truly random and unpredictable, then the universe operates according to probabilistic rather than deterministic principles. This fundamental randomness might provide the physical basis for free will, suggesting that conscious beings can influence quantum outcomes through their choices and intentions. Some interpretations of quantum mechanics propose that consciousness and quantum measurement are intimately connected through information processing. In this view, conscious observation involves the irreversible recording of information about quantum states, which triggers wave function collapse and determines physical outcomes. The brain might serve as a sophisticated quantum information processor that interfaces with quantum systems through measurement-induced state reductions. The delayed choice quantum eraser experiments demonstrate that quantum tunneling behavior can be influenced by measurements made after the tunneling event has already occurred. These experiments suggest that the past and future might be more interconnected than classical physics allows, with future measurements retroactively determining the history of quantum systems. This temporal non-locality challenges our basic assumptions about the arrow of time and causality. Quantum error correction mechanisms in natural systems reveal how the universe maintains stable information processing despite the inherent randomness of quantum tunneling events. Biological systems appear to exploit quantum error correction to preserve genetic information and maintain metabolic stability. These natural quantum computers might provide templates for understanding how consciousness interfaces with quantum systems. The relationship between quantum tunneling and thermodynamics raises questions about the fundamental nature of entropy and information. Quantum tunneling can enable systems to explore configuration spaces that would be inaccessible through classical thermal processes, potentially allowing for violations of classical thermodynamic principles. These quantum effects might explain how life maintains low entropy states in apparent violation of the second law of thermodynamics. Modern experiments in quantum foundations continue to probe the mysteries of measurement and tunneling with increasing precision. Quantum non-demolition measurements allow scientists to observe quantum systems without destroying their coherence, enabling the study of quantum superposition and tunneling in real time. These experiments reveal the delicate balance between quantum coherence and classical definiteness that governs all physical phenomena. The development of quantum technologies forces us to confront the practical implications of quantum measurement mysteries. Quantum computers must maintain coherent superposition states while performing calculations, requiring unprecedented control over environmental decoherence. The success of these technologies demonstrates that the strange features of quantum mechanics aren't merely philosophical curiosities, but represent fundamental aspects of reality that can be harnessed for practical applications. Quantum tunneling microscopy reveals how quantum measurement affects individual atoms and molecules. These instruments can observe quantum superposition states at the single particle level, providing direct evidence for the reality of quantum mechanical phenomena. The images they produce show individual atoms flickering between different quantum states, offering glimpses into the probabilistic foundations of matter itself. The study of quantum tunneling in artificial quantum systems allows researchers to explore the boundary between quantum and classical behavior under controlled conditions. These experiments reveal how environmental factors influence the transition from quantum to classical physics, providing insights into the mechanisms that govern wave function collapse and measurement-induced state reduction. As we grapple with these profound mysteries, we're confronted with the possibility that reality itself might be far more fluid and participatory than our everyday experience suggests. Quantum tunneling events occur continuously throughout the universe, each one representing a moment where the impossible becomes real through processes that transcend classical logic. The mathematics that describe these phenomena work with extraordinary precision, yet the physical interpretation remains deeply mysterious. The deepest implications of quantum tunneling might extend beyond physics into the realm of consciousness and meaning. If quantum measurement requires conscious observation to determine outcomes, then awareness itself becomes a fundamental feature of physical reality. The act of observation doesn't just reveal pre-existing properties. It participates in creating the very reality we observe, making consciousness an active partner in the cosmic dance of existence. Chapter 6. Life, Death, and Quantum Resurrection. Life exists at the most remarkable intersection in the universe. The delicate boundary where quantum mechanics meets classical physics, where the impossible becomes not just possible, but essential for survival itself. Every breath you take, every thought that crosses your mind, every heartbeat that sustains your existence, depends on quantum tunneling events occurring billions of times per second within the molecular machinery of your cells. Without these quantum effects, the chemistry of life would grind to a halt, leaving behind a universe of sterile simplicity, where complex biological structures could never emerge. The discovery of quantum effects in biological systems has revolutionized our understanding of how life operates at its most fundamental level. For decades, scientists assumed that the warm, wet, noisy environment inside living cells would instantly destroy any quantum coherence, making quantum effects irrelevant to biology. The assumption seemed reasonable. Quantum phenomena typically require the pristine conditions of laboratory experiments, with temperatures near absolute zero and isolation from environmental disturbances. Yet nature appears to have evolved sophisticated mechanisms for protecting and exploiting quantum effects even in the chaotic thermal environment of living systems. Enzymes, the molecular machines that catalyze nearly every chemical reaction in your body, rely heavily on quantum tunneling to function with the extraordinary efficiency that life demands. These protein structures create carefully controlled quantum environments where tunneling can occur reliably despite the surrounding molecular turmoil. Enzyme catalysis represents one of the most elegant examples of biological quantum tunneling. Many enzymatic reactions involve the transfer of hydrogen atoms, protons, or electrons across energy barriers that would be insurmountable through classical thermal activation alone. The barriers exist because of the complex three-dimensional geometry of protein active sites, which position reactant molecules in precise orientations that favor specific chemical transformations. Consider the enzyme alcohol dehydrogenase, which helps your liver process alcoholic beverages by transferring hydrogen atoms between molecules. The reaction involves moving a hydrogen atom from an alcohol molecule to a cofactor called nicotinamide adenine dinucleotide. Classical chemistry would predict that this transfer requires sufficient thermal energy to lift the hydrogen atom over the energy barrier, separating the initial and final states. However, careful kinetic studies reveal that the reaction proceeds much faster than classical theory allows, particularly at low temperatures, where thermal energy becomes insufficient for barrier crossing. The explanation lies in quantum tunneling. The hydrogen atom, despite its relatively large mass compared to electrons, can tunnel through the energy barrier created by the enzyme's active site geometry. The protein structure precisely positions the donor and acceptor molecules to optimize tunneling probability, creating what biochemists call a tunneling-ready configuration. The enzyme doesn't just lower activation barriers through binding effects. It creates quantum mechanical pathways that allow reactions to proceed through tunneling processes. Temperature-dependent studies of enzymatic reactions provide compelling evidence for biological quantum tunneling. Classical chemical reactions show exponential dependence on temperature, following the Arrhenius equation that relates reaction rates to thermal activation energy. Quantum tunneling reactions, however, show much weaker temperature dependence, because tunneling probability depends on barrier thickness and particle mass rather than thermal energy. Many enzymes exhibit kinetic isotope effects that strongly support quantum tunneling mechanisms. When researchers replace hydrogen atoms with deuterium, hydrogen's heavier isotope, reaction rates decrease dramatically, often by factors of 10 to 50. This isotope effect is much larger than classical chemistry would predict, but matches beautifully with quantum mechanical calculations of tunneling probability for particles with different masses. The enzyme methylamine dehydrogenase provides a particularly striking example of biological quantum tunneling. This enzyme transfers electrons over distances of several angstroms through a series of protein-bound cofactors. The electron transfer occurs much faster than classical electron transport theory predicts, requiring quantum tunneling through the protein matrix that separates electron donor and acceptor sites, Photosynthesis, the process that converts sunlight into chemical energy and sustains virtually all life on Earth, exploits quantum effects with remarkable sophistication. Recent discoveries reveal that photosynthetic systems maintain quantum coherence for surprisingly long periods, allowing energy to explore multiple pathways simultaneously before selecting the most efficient route to reaction centers where chemical conversion occurs. The light harvesting complexes in photosynthetic organisms create quantum superposition states where excitation energy exists simultaneously across multiple chlorophyll molecules. This quantum coherence enables nearly perfect energy transfer efficiency, approaching theoretical limits that classical systems cannot achieve. The energy doesn't follow a single path from antenna molecules to reaction centers. It explores all possible pathways simultaneously through quantum superposition, automatically selecting the most efficient route. Quantum tunneling also plays crucial roles in the electron transport chains that generate adenosine triphosphate, the universal energy currency of life. These molecular assembly lines pass electrons through a series of protein complexes embedded in cellular membranes. Each electron transfer step involves quantum tunneling across protein barriers that would block classical electron flow. The enzyme cytochrome C oxidase, which catalyzes the final step of cellular respiration, demonstrates how evolution has optimized protein structures for quantum tunneling efficiency. The enzyme contains carefully positioned metal centers that create optimal tunneling distances for electron transfer. Mutations that alter these distances dramatically reduce enzyme activity, showing how precisely biology must control quantum mechanical parameters. DNA replication and repair processes depend critically on quantum tunneling events that enable base pairing and chemical modification reactions. The hydrogen bonds that hold DNA strands together involve proton tunneling between complementary bases. Occasionally, protons tunnel to incorrect positions, creating mismatched base pairs that can lead to genetic mutations if not corrected by cellular repair mechanisms. Quantum tunneling in DNA provides one mechanism for evolutionary change through spontaneous mutation. The double helix structure positions protons in hydrogen bonds where tunneling between alternative configurations can occur spontaneously. While DNA repair systems correct most of these quantum-induced errors, some persist and contribute to the genetic variation that drives evolutionary adaptation. Bird navigation represents one of the most spectacular examples of quantum effects in biological systems. Many migratory birds possess magnetic sensing capabilities that appear to rely on quantum entanglement between electrons and specialized proteins called cryptochromes. These proteins are located in the bird's retinas, suggesting that magnetic navigation might involve quantum processes occurring directly within their visual system. The proposed mechanism involves the formation of entangled electron pairs when light strikes cryptochrome molecules. Earth's magnetic field influences the quantum states of these entangled electrons, creating subtle changes in chemical reaction rates that the bird's nervous systems can detect. This quantum compass provides directional information that supplements other navigation cues like visual landmarks and celestial bodies. Quantum effects in the nervous system itself remain an active area of research and speculation. Some theories propose that consciousness emerges from quantum processes occurring within neural microtubules, the protein structures that provide cellular scaffolding. These theories suggest that quantum coherence in neural systems might enable the unity and binding properties that characterize conscious experience. The olfactory system provides another potential example of biological quantum effects. The ability to distinguish between molecules with identical structures, but different quantum vibrational states suggests that smell detection might involve quantum tunneling processes. When odor molecules bind to receptor proteins, electrons might tunnel between molecular orbitals in ways that depend on the molecule's vibrational quantum states. Enzymatic reactions in metabolic pathways often involve quantum tunneling of protons and hydride ions across substantial energy barriers. The enzyme dihydrofolate reductase, essential for DNA synthesis, demonstrates how protein dynamics create fleeting opportunities for quantum tunneling. The enzyme undergoes conformational changes that briefly bring donor and acceptor atoms close enough for efficient tunneling to occur. Quantum effects also influence the folding of proteins into their functional three-dimensional structures. The process involves navigating complex energy landscapes where multiple folding pathways compete. Quantum tunneling might enable proteins to escape from kinetic traps that would otherwise prevent proper folding, helping to explain how large proteins fold reliably, despite the astronomical number of possible misfolded configurations. The maintenance of biological quantum coherence requires sophisticated molecular mechanisms that protect quantum states from environmental decoherence. Living systems appear to have evolved protein scaffolds that create local environments where quantum effects can persist long enough to influence biological outcomes. These protective mechanisms might involve carefully controlled water structures, specific amino acid arrangements, or dynamic protein motions that refresh quantum coherence. Temperature plays a crucial role in biological quantum effects, with many quantum processes showing optimal functionality at physiological temperatures around 37 degrees Celsius. This suggests that evolution has fine-tuned biological quantum systems to operate efficiently within the thermal constraints imposed by liquid-water chemistry. The study of quantum effects in extremophile organisms reveals how life adapts quantum processes to unusual environmental conditions. Organisms living in high-temperature environments like deep-sea thermal vents might exploit different quantum mechanisms than those operating in more moderate conditions. These adaptations provide insights into the flexibility and robustness of biological quantum systems. Artificial photosynthetic systems inspired by biological quantum effects represent promising approaches for renewable energy technology. Understanding how natural photosynthesis achieves nearly perfect quantum efficiency guides the development of artificial light harvesting devices that could revolutionize solar energy conversion. The intersection of quantum biology and medicine opens new possibilities for understanding disease processes and developing therapeutic interventions. Some diseases might involve disruption of normal quantum processes in cellular systems, suggesting that treatments could target quantum mechanical aspects of biological function. As we contemplate the quantum foundations of life, we're reminded that the boundary between living and non-living matter might be more subtle than classical biology suggests. Life doesn't simply exploit classical physics with greater complexity. It operates as a quantum system that has learned to maintain coherence and harness quantum effects for survival and reproduction. The warm, wet chemistry of biological systems provides not just a medium for life, but a carefully evolved quantum laboratory where the impossible becomes routine, where tunneling events enable the molecular dances that sustain consciousness itself. Chapter 7. The Universe as a Quantum Computer. Empty Space. The vast expanses between stars and galaxies that appear to contain nothing at all seethes with quantum activity so intense and fundamental that it might hold the key to understanding the ultimate fate of reality itself. What we perceive as perfect vacuum actually represents one of the most dynamic arenas in the universe, where virtual particles constantly flicker in and out of existence, where quantum fields fluctuate with energies that dwarf the output of entire galaxies, and where quantum tunneling might enable transitions so dramatic they could reshape the very laws of physics. The quantum vacuum represents far more than simple emptiness. According to quantum field theory, every point in space contains energy fields that undergo constant fluctuations, creating temporary particle-antiparticle pairs that annihilate almost immediately after their creation. These vacuum fluctuations occur even at absolute zero temperature, representing the irreducible quantum mechanical zero-point energy that permeates all of space. The energy density of quantum vacuum fluctuations challenges our understanding of physics in profound ways. When physicists attempt to calculate the total energy stored in quantum fields, they encounter infinities that appear to have no physical meaning. These infinities must be carefully regulated through mathematical procedures that remain somewhat mysterious, suggesting that our understanding of vacuum energy remains fundamentally incomplete. Recent theoretical work suggests that empty space itself might exist in what physicists call a false vacuum state, a configuration that appears stable but actually represents a local minimum in a more complex energy landscape. If this hypothesis proves correct, then the entire universe might be susceptible to a quantum tunneling transition that could fundamentally alter the nature of a physical reality throughout all of space and time. The false vacuum hypothesis emerges from attempts to understand the relationship between different fundamental forces and the particles they govern. The standard model of particle physics describes these relationships through quantum field theory, where particle properties emerge from the dynamics of underlying fields that permeate space. The vacuum state represents the ground state of these fields, but quantum field theory allows for the possibility that apparent ground states might actually be excited, states of deeper, more fundamental configurations. Consider what would happen if our vacuum underwent a quantum tunneling transition to a lower energy state. The process would begin at some random point in space, where quantum fluctuations create a small bubble of true vacuum within the surrounding false vacuum. This bubble would possess different physical properties than the space around it, different particle masses, altered force strengths, perhaps even different numbers of spatial dimensions. The boundary between true and false vacuum regions would expand at the speed of light, driven by the energy difference between the two states. As this boundary swept through space, it would convert everything in its path to the new vacuum configuration. Stars, planets, and all the complex structures built from matter as we know it would be instantly transformed or destroyed as the fundamental parameters governing physics shifted to their new values. The expansion of such a vacuum bubble would be absolutely unstoppable by any physical process, since information about the approaching boundary could not travel faster than the boundary itself. Entire galaxies would be converted to the new physics without any possibility of advance warning or defensive measures. The transition would propagate throughout the observable universe and beyond, potentially transforming infinite volumes of space. This scenario represents perhaps the most complete form of destruction imaginable, not merely the annihilation of matter and energy, but the elimination of the very physical laws that govern their behavior. The new vacuum state might support entirely different types of particles and forces, creating a universe so alien that concepts like atoms, chemistry, and biological evolution might become meaningless. Yet the mathematical framework that describes vacuum decay also provides reasons for cautious optimism about the stability of our current universe. The quantum tunneling probability for vacuum transitions depends on the same exponential factors that govern all tunneling processes. If the energy barrier separating false vacuum from true vacuum is sufficiently high, the tunneling rate becomes so slow that vacuum decay events would be extraordinarily rare. Current estimates suggest that if our universe does exist in a false vacuum state, the time scale for vacuum decay vastly exceeds the current age of the universe. The probability of spontaneous vacuum decay occurring anywhere in the observable universe during the next billion years might be negligible compared to other cosmic catastrophes like gamma-ray bursts or asteroid impacts. The cosmic microwave background radiation provides indirect constraints on vacuum stability by revealing that the universe has maintained consistent physical laws for nearly 14 billion years. If vacuum decay were occurring frequently on cosmic scales, we would observe evidence of regions with altered physics in the fossil radiation left over from the early universe. The remarkable uniformity of this background radiation suggests that vacuum decay events, if they occur at all, must be extraordinarily rare. Quantum tunneling also plays crucial roles in scenarios for the birth and evolution of the universe itself. During cosmic inflation, the rapid expansion that occurred during the first fraction of a second after the Big Bang, quantum tunneling might have enabled transitions between different vacuum states that determined the ultimate structure and properties of space-time. The inflationary epoch represents a period when quantum fluctuations in vacuum energy fields became amplified to macroscopic scales, creating the seeds for galaxy formation and large-scale structure throughout the universe. These fluctuations involved quantum tunneling processes occurring in the extreme conditions present during the earliest moments of cosmic history. Some cosmological models propose that our universe emerged from a quantum tunneling event in a pre-existing space-time. In these scenarios, the Big Bang represents not the absolute beginning of existence, but rather a transition from one vacuum state to another, with our observable universe representing a bubble of space-time that nucleated through quantum tunneling and subsequently expanded to its current size. The relationship between quantum tunneling and black hole physics reveals additional layers of complexity in our understanding of vacuum structure. Stephen Hawking's discovery that black holes emit thermal radiation through quantum effects near their event horizons demonstrates that even the most extreme gravitational fields cannot completely suppress quantum fluctuations in vacuum fields. Hawking radiation emerges from quantum tunneling processes occurring near black hole event horizons, where virtual particle pairs separate before they can annihilate. One member of each pair falls into the black hole, while the other escapes as real radiation, slowly draining the black hole's mass and energy. This process represents a form of quantum tunneling, where information and energy escape from regions of space-time that classical physics declares absolutely isolated. The information paradox associated with black hole evaporation raises profound questions about the preservation of quantum information during tunneling processes. If information about matter falling into black holes is eventually recovered through Hawking radiation, then quantum tunneling must preserve detailed information about quantum states, even when those states undergo extreme transformations. Holographic theories of quantum gravity suggest that information about three-dimensional volumes of space can be completely encoded on two-dimensional boundary surfaces. From this perspective, quantum tunneling might represent information processing operations occurring on the holographic boundaries that define space-time regions. The apparent three-dimensional motion of particles through barriers might reflect computational processes occurring in lower-dimensional holographic representations. The holographic principle implies that reality, as we experience it, might emerge from information processing, occurring in hidden computational substrates. Quantum tunneling events throughout the universe could represent elementary computational operations in a vast information processing system that generates the appearance of physical reality through holographic projection mechanisms. These speculative connections between quantum tunneling and information processing suggest that the universe itself might operate as a quantum computer of unimaginable complexity. Every quantum tunneling event, from stellar fusion reactions to electronic processes in biological systems, might represent computational steps in cosmic algorithms that generate the patterns we observe as physical laws and material structures. The computational perspective on quantum tunneling provides new ways of understanding the relationship between physical processes and information. Classical physics treats information as secondary to matter and energy, but quantum mechanics suggests that information might be the fundamental currency from which physical properties emerge through information processing operations. Quantum error correction mechanisms in natural systems demonstrate how the universe maintains stable information processing, despite the inherent randomness of quantum tunneling events. These mechanisms ensure that crucial information about physical laws and particle properties remains preserved even when individual quantum events introduce apparent errors or uncertainties. The development of quantum computers provides practical tools for testing theories about the computational nature of physical reality. These devices exploit controlled quantum tunneling to perform calculations that would be impossible with classical computers, potentially revealing deep connections between information processing and fundamental physics. As quantum computers become more sophisticated, they might enable simulations of vacuum decay processes and other extreme quantum phenomena that cannot be studied through direct experimentation. These simulations could provide insights into the stability of our vacuum state and the likelihood of transitions to alternative physics. The relationship between consciousness and quantum information processing opens additional speculative possibilities for understanding the role of quantum tunneling in generating subjective experience. If consciousness emerges from quantum computational processes, then the tunneling events occurring throughout biological systems might contribute directly to the generation of awareness and subjective experience. Advanced civilizations might develop technologies that exploit vacuum structure and quantum tunneling for purposes we can barely imagine. Controlled vacuum transitions could potentially enable faster-than-light communication or travel through the manipulation of space-time geometry at quantum scales. The energy released by vacuum decay processes might provide power sources that dwarf anything achievable through conventional matter-antimatter annihilation. The ultimate implications of quantum tunneling for cosmic evolution remain deeply mysterious. We inhabit a universe where the fundamental vacuum state might be unstable, where reality itself could undergo phase transitions that rewrite the laws of physics. Yet, the same quantum instability enables the fusion reactions that power stars, the chemical processes that sustain life, and perhaps the information processing operations that generate consciousness itself. The study of vacuum decay and quantum tunneling confronts us with the possibility that stability and permanence might be illusions created by our limited perspective on cosmic timescales. The physical laws we consider eternal and unchanging might represent temporary configurations in a much larger space of possibilities, maintained only by quantum mechanical barriers that could be penetrated through tunneling processes occurring over vast periods of time. Chapter 8. Macroscopic Tunneling and the Future of Reality. The boundary between the quantum and classical worlds has long been considered inviolable, a fundamental divide separating the strange realm of subatomic particles from the familiar territory of everyday objects. Yet recent experiments are pushing this boundary to its breaking point, revealing that quantum effects like tunneling might not be forever confined to the microscopic scale. Scientists around the world are now attempting to coax larger and larger objects into exhibiting quantum behavior, including quantum tunneling, with implications that could revolutionize our understanding of the limits of quantum mechanics. The quest to observe macroscopic quantum tunneling began with a simple question: at what point do quantum effects disappear as objects become larger and more complex? For decades, physicists assumed that quantum coherence would be destroyed almost instantly in objects containing more than a few dozen atoms. The warm, noisy environment of the macroscopic world seemed fundamentally incompatible with the delicate quantum states that enable tunneling and other quantum phenomena. This assumption began to crumble in the late 20th century as experimenters developed increasingly sophisticated techniques for isolating quantum systems from environmental disturbances. Superconducting circuits cooled to millikelvin temperatures could maintain quantum coherence across relatively large structures containing billions of atoms. These systems demonstrated that size alone doesn't necessarily destroy quantum behavior if environmental decoherence can be sufficiently suppressed. The development of cavity quantum electrodynamics opened new possibilities for studying quantum effects in mesoscopic systems, objects larger than individual atoms but smaller than classical mechanical devices. Researchers learned to trap individual atoms in optical cavities where they could interact with single photons while remaining isolated from external perturbations. These experiments revealed that carefully controlled environments could preserve quantum coherence over much larger scales than previously thought possible. Josephson junctions in superconducting circuits provided early examples of macroscopic quantum tunneling in artificial systems. These devices consist of two superconductors separated by thin insulating barriers through which Cooper pairs of electrons can tunnel. When cooled to sufficiently low temperatures, entire Josephson junctions can exist in quantum superposition states where macroscopic currents flow simultaneously in opposite directions through quantum tunneling processes. The observation of macroscopic quantum tunneling in superconducting quantum interference devices marked a watershed moment in quantum physics. These devices contain superconducting loops interrupted by Josephson junctions, creating systems where magnetic flux can tunnel between different quantized states. The tunneling involves collective motion of billions of electrons, yet the quantum mechanical description remains valid and experimentally verifiable. More recent experiments have pushed the boundaries of macroscopic quantum behavior even further, using mechanical oscillators coupled to quantum systems. Researchers have demonstrated quantum superposition and entanglement in objects visible to the naked eye, including vibrating membranes and oscillating cantilevers that contain trillions of atoms. While these experiments haven't yet achieved true quantum tunneling of macroscopic objects, they establish the experimental foundations necessary for such observations. The theoretical framework for macroscopic quantum tunneling builds on the same mathematical foundations that describe atomic-scale quantum effects. The key insight is that tunneling probability depends exponentially on the action associated with the tunneling process, which scales with both the mass of the tunneling object and the distance it must traverse. For macroscopic objects, these factors conspire to make tunneling probabilities vanishingly small under normal circumstances. However, carefully engineered systems can create conditions where macroscopic quantum tunneling becomes observable over reasonable experimental timescales. The strategy involves minimizing the effective action by reducing the tunneling distance, lowering the energy barriers, and creating symmetric potential wells where tunneling can occur between nearly degenerate quantum states. One of the most promising approaches involves graphene membranes suspended over metallic substrates. Graphene's remarkable mechanical properties allow the creation of membranes just 1 atom thick that can span distances of several micrometers. When voltage is applied between the membrane and substrate, the graphene can exist in 2 stable configurations: slightly bowed upward or pressed against the substrate below. The transition between these configurations involves collective motion of millions of carbon atoms. Yet, quantum tunneling between the 2 states becomes possible under carefully controlled conditions. The tunneling probability depends on the membrane size, the applied voltage, and the temperature of the system. Theoretical calculations suggest that observable tunneling rates could be achieved in membranes cooled to millikelvin temperatures. Experimental verification of macroscopic quantum tunneling in graphene membranes requires extraordinarily sensitive measurement techniques capable of detecting changes in membrane configuration without destroying quantum coherence. Researchers use capacitance measurements to monitor the membrane's position, since the electrical capacitance between membrane and substrate changes dramatically when the membrane switches between its 2 stable states. The challenge lies in performing these measurements with sufficient sensitivity to detect tunneling events while avoiding the back action that measurement typically imposes on quantum systems. Quantum non-demolition measurement techniques allow researchers to monitor system properties without collapsing quantum superposition states, enabling real-time observation of quantum tunneling dynamics in macroscopic systems. Alternative approaches to macroscopic quantum tunneling involve magnetic systems where collective spin orientations can tunnel between different configurations. Magnetic molecules containing hundreds of atoms can exhibit tunneling between spin-up and spin-down states, with the tunneling involving coherent reorientation of magnetic moments throughout the entire molecular structure. Single-molecule magnets provide particularly elegant examples of macroscopic quantum tunneling in magnetic systems. These molecules contain clusters of magnetic atoms that couple together to create large total magnetic moments. At low temperatures, the thermal energy becomes insufficient to flip these magnetic moments over energy barriers, but quantum tunneling allows transitions between different magnetic orientations. The study of magnetic quantum tunneling has revealed unexpected quantum effects in systems traditionally considered classical. Magnetic domain walls in ferromagnetic materials can tunnel through energy barriers, enabling magnetic switching processes that would be impossible through classical thermal activation. These effects have important implications for magnetic data storage technologies and spintronic devices. Levitated nanoparticles represent another frontier in macroscopic quantum physics, with potential applications to quantum tunneling studies. Optical or magnetic trapping allows individual nanoparticles to be isolated from environmental disturbances while remaining accessible to experimental manipulation. These systems could potentially demonstrate quantum tunneling of entire nanoparticles between different trap locations. The Experimental requirements for observing macroscopic quantum tunneling push current technology to its limits. Ultra-high vacuum systems eliminate molecular collisions that would destroy quantum coherence. Vibration isolation systems prevent mechanical disturbances from coupling to the quantum system. Electromagnetic shielding blocks external fields that could induce decoherence through unwanted interactions. Temperature control represents perhaps the most critical experimental parameter for macroscopic quantum tunneling studies. Thermal fluctuations provide the primary source of decoherence in mesoscopic systems, so experiments typically require cooling to temperatures below 1 Kelvin. Dilution refrigerators capable of reaching microkelvin temperatures provide the necessary thermal isolation for quantum coherence to survive in large systems. The technological implications of successful macroscopic quantum tunneling demonstrations extend far beyond fundamental physics into practical applications for quantum information processing and sensing. Macroscopic quantum systems could serve as highly sensitive detectors for gravitational waves, dark matter particles, or other exotic phenomena that couple weakly to ordinary matter. Quantum computers based on macroscopic quantum systems might offer advantages over current approaches that rely on atomic-scale qubits. Larger quantum systems could potentially be more robust against certain types of environmental noise, while remaining controllable through macroscopic electromagnetic fields. The engineering challenges would be substantial, but the potential benefits could justify the development effort. The study of macroscopic quantum tunneling also provides new perspectives on the quantum to classical transition that governs the emergence of classical physics from quantum foundations. Understanding exactly how and why quantum effects disappear as systems become larger could illuminate fundamental questions about the nature of physical reality and the role of measurement in quantum mechanics. Decoherence theory predicts that macroscopic quantum tunneling should become increasingly difficult to observe as system size increases, but the precise scaling laws remain subjects of active research. Experimental tests of these scaling relationships could reveal whether there are fundamental limits to the size of objects that can exhibit quantum behavior, or whether sufficiently sophisticated isolation techniques could preserve quantum effects in arbitrarily large systems. The philosophical implications of macroscopic quantum tunneling challenge our intuitive understanding of the relationship between quantum and classical physics. If large objects can tunnel through barriers, then the classical world we experience daily might be more quantum mechanical than we realize. The apparent solidity and determinism of macroscopic objects could represent statistical averages over enormous numbers of underlying quantum processes. Future experiments in macroscopic quantum tunneling might explore the limits of quantum mechanics itself by testing whether quantum superposition states can be maintained in progressively larger and more complex systems. These experiments could provide crucial tests of proposed modifications to quantum mechanics that predict the breakdown of quantum behavior above certain mass scales. The development of room temperature quantum effects represents a long-term goal that could transform quantum technologies from laboratory curiosities into practical devices for everyday use. While current macroscopic quantum tunneling experiments require extreme isolation from environmental disturbances, future advances might reveal ways to protect quantum coherence even under ambient conditions. Biological systems provide inspiration for robust quantum effects operating in warm, noisy environments. The quantum effects observed in photosynthesis and other biological processes suggest that nature has evolved sophisticated mechanisms for maintaining quantum coherence despite thermal fluctuations and molecular collisions. Understanding these biological quantum protection mechanisms could guide the development of artificial systems with similar robustness. As we stand on the threshold of potentially observing quantum tunneling in objects visible to the naked eye, we're reminded that the boundary between the quantum and classical worlds remains far more fluid than our everyday experience suggests. The same mathematical principles that govern electron tunneling in atomic systems also apply to much larger objects, revealing the universal nature of quantum mechanics across all scales of physical reality. The challenge lies not in the fundamental physics, but in creating experimental conditions where these universal principles can manifest in ways we can directly observe and control. Chapter 9. The Consciousness Connection. The relationship between consciousness and quantum mechanics represents one of the most profound and controversial frontiers in modern science, where the act of observation itself appears to play a fundamental role in determining physical reality. When we examine quantum tunneling through the lens of consciousness studies, we encounter possibilities so extraordinary that they challenge our most basic assumptions about the nature of mind, matter, and the relationship between observer and observed. The observer effect in quantum mechanics suggests that conscious measurement fundamentally alters the behavior of quantum systems. In quantum tunneling experiments, the very act of trying to determine whether a particle has tunneled through a barrier appears to influence the tunneling process itself. This isn't simply a matter of clumsy experimental technique disturbing delicate quantum systems. The mathematics of quantum mechanics seem to require conscious observation as an integral component of physical reality. Consider what happens when we attempt to monitor a quantum tunneling event in real time. Before measurement, quantum mechanics describes the particle as existing in a superposition of states simultaneously, exploring all possible paths through the experimental apparatus. The particle doesn't have a definite location or a determined history until the moment we perform a measurement to detect its presence on one side of the barrier or the other. The mathematical formalism suggests that measurement causes the quantum wave function to collapse instantaneously from a state of multiple possibilities to a single definite outcome. This collapse appears to occur faster than light could travel between different parts of the experimental apparatus, implying that quantum measurement involves non-local effects that transcend ordinary space and time. The consciousness of the observer seems to play a crucial role in triggering this collapse and determining which of many possible outcomes becomes real. Yet, the precise mechanism by which consciousness interfaces with quantum systems remains deeply mysterious. Some interpretations of quantum mechanics propose that consciousness possesses unique properties that allow it to reduce quantum wave functions through purely mental processes. In this view, conscious observation doesn't simply reveal pre-existing properties of quantum systems. It actively participates in creating the reality we observe through the act of measurement. The hard problem of consciousness, explaining how subjective experience arises from objective physical processes, takes on new dimensions when viewed through the lens of quantum mechanics. If consciousness can influence quantum systems through observation, then mental states might possess causal powers that transcend the normal boundaries between mind and matter. Subjective experience could represent a fundamental feature of reality rather than an emergent property of complex neural computation. Quantum theories of consciousness propose that awareness itself emerges from quantum processes occurring within biological systems. These theories suggest that the brain operates as a quantum computer, with neural networks maintaining quantum coherence across scales much larger than previously thought possible. Quantum tunneling events within neural microtubules, or synaptic junctions, might provide the physical basis for conscious experience and cognitive processing. Roger Penrose and Stuart Hameroff developed one of the most detailed quantum theories of consciousness, proposing that quantum computations in neural microtubules generate conscious experience through a process called orchestrated objective reduction. In their model, quantum superposition states within microtubular proteins maintain coherence long enough to perform quantum computations before collapsing into classical states that trigger neural firing patterns. The Penrose-Hameroff theory suggests that consciousness involves quantum tunneling processes occurring within the protein, structures that provide cellular scaffolding throughout the nervous system. These tunneling events might enable quantum information processing capabilities that transcend the computational limits of classical neural networks, potentially explaining the remarkable efficiency and creativity of human cognitive processes. However, mainstream neuroscience remains skeptical of quantum theories of consciousness, arguing that the warm, wet environment of the brain would destroy quantum coherence almost instantly through decoherence processes. The thermal energy present at body temperature seems more than sufficient to disrupt the delicate quantum states that these theories require for conscious experience. Critics point out that no convincing experimental evidence yet demonstrates quantum coherence in neural systems under physiological conditions. Despite these criticisms, recent discoveries of quantum effects in biological systems provide renewed support for quantum approaches to consciousness. The observation of quantum coherence in photosynthetic systems, bird navigation, and enzymatic processes demonstrates that biological systems can maintain and exploit quantum effects even in warm, noisy environments. These findings suggest that evolution might have developed sophisticated mechanisms for protecting quantum coherence in living systems. The global workspace theory of consciousness offers another perspective on how quantum effects might contribute to conscious experience. This theory proposes that consciousness emerges when information becomes globally accessible throughout different brain regions through neural broadcasting mechanisms. Quantum tunneling could potentially enable the rapid, long-range correlations necessary for global workspace integration. Integrated information theory provides yet another framework for understanding consciousness that might accommodate quantum effects. This theory measures consciousness in terms of the integrated information generated by neural networks, with higher levels of integration corresponding to richer conscious experiences. Quantum tunneling and entanglement might enable forms of information integration that exceed the capabilities of classical neural networks. The relationship between free will and quantum indeterminacy represents another fascinating intersection between consciousness and quantum mechanics. If conscious decisions involve quantum processes, then the fundamental randomness of quantum events might provide the physical basis for genuine free will. Quantum tunneling in neural systems could introduce sufficient indeterminacy to allow conscious beings to influence their own brain states through purely mental processes. However, random quantum events don't necessarily constitute free will in any meaningful sense. True free will would require conscious control over quantum processes rather than simple randomness. Some theories propose that consciousness might bias quantum outcomes without completely determining them, creating a form of influenced randomness that preserves both causal efficacy and genuine choice. The delayed choice quantum eraser experiments reveal temporal aspects of quantum measurement that challenge our understanding of causality and consciousness. These experiments demonstrate that measurements made after quantum events have already occurred can retroactively determine the history of those events. If conscious observation plays a role in quantum measurement, then consciousness might possess backward in time causal powers that influence past quantum states. The implications of backward causation for consciousness studies are profound and disturbing. Conscious decisions made in the present might influence past quantum events, creating causal loops that challenge our basic understanding of temporal sequence and personal identity. The act of remembering past events might literally create the quantum mechanical history that generated those memories in the first place. Quantum entanglement provides another mechanism through which consciousness might transcend the normal boundaries of space and time. If conscious observers can become quantum mechanically entangled with the systems they study, then consciousness might gain access to non-local correlations that enable instantaneous communication across arbitrary distances. Some researchers have proposed that telepathic phenomena might involve quantum entanglement between conscious minds. The measurement problem in quantum mechanics becomes even more perplexing when consciousness is considered as a potential solution. If conscious observation causes wave function collapse, then consciousness must possess non-physical properties that can interface with quantum systems without being described by quantum mechanics itself. This suggests a form of dualism where mental processes operate according to principles fundamentally different from physical laws. Alternative interpretations of quantum mechanics offer different perspectives on the role of consciousness in quantum processes. The many-worlds interpretation eliminates wave function collapse entirely, suggesting that all possible quantum outcomes occur simultaneously in parallel branches of reality. From this perspective, consciousness doesn't influence quantum events, but rather selects which branch of the multiverse conscious observers experience. The consistent histories interpretation focuses on the information that can be consistently extracted from quantum systems rather than the role of conscious observers. In this framework, quantum tunneling events possess definite histories whether or not conscious beings observe them, with consciousness serving as one among many possible information extraction mechanisms, rather than a special collapse-inducing agent. Quantum information theory provides tools for analyzing the relationship between consciousness and quantum mechanics in terms of information processing capabilities. Conscious observers might represent sophisticated quantum information processors capable of extracting and manipulating quantum information in ways that classical systems cannot achieve. The brain could serve as a biological quantum computer that interfaces with quantum systems through information theoretic rather than purely physical mechanisms. The study of anesthesia offers intriguing clues about the relationship between consciousness and quantum effects. Anesthetic agents that eliminate conscious experience might work by disrupting quantum processes in neural systems. Some anesthetics appear to interfere with quantum tunneling in neural proteins, suggesting that conscious awareness might indeed depend on quantum mechanical processes within the brain. Psychedelic research provides another window into consciousness that might illuminate quantum aspects of mental experience. Compounds like psilocybin and lysergic acid diethylamide appear to alter conscious experience in ways that might involve quantum effects in neural systems. The dramatic changes in perception and cognition produced by these substances could reflect alterations in quantum information processing within the brain. The development of brain-computer interfaces raises questions about how technological systems might interface with quantum aspects of consciousness. if conscious experience involves quantum processes, then effective brain-computer integration might require quantum mechanical coupling between biological and artificial systems. Such interfaces could potentially extend conscious awareness into quantum computational substrates. As we contemplate these possibilities, we must remain mindful of the speculative nature of consciousness quantum connections. While the mathematical formalism of quantum mechanics appears to require conscious observation for wave-function collapse, the physical mechanisms underlying this requirement remain completely mysterious. Current neuroscience provides no convincing evidence for quantum coherence in neural systems under normal physiological conditions. Yet, the questions raised by quantum consciousness theories demand serious consideration, even if current evidence remains inconclusive. The relationship between mind and matter represents one of the deepest mysteries in science, and quantum mechanics provides the only known physical framework where consciousness appears to play a fundamental role in determining objective reality. Whether consciousness truly influences quantum systems, or whether these apparent connections reflect deeper misunderstandings about the nature of both consciousness and quantum mechanics, remains one of the most important open questions in contemporary science. The intersection of consciousness and quantum tunneling thus represents a frontier where our most fundamental assumptions about reality encounter their greatest challenges, where the solid boundaries between observer and observed, between mind and matter, begin to dissolve into something far more fluid and mysterious than our everyday experience suggests. Chapter 10. When reality debugs itself, the universe appears to possess an extraordinary capacity for self-correction, maintaining remarkable stability and consistency, despite the inherent randomness and uncertainty that characterize quantum mechanical processes at its foundation. Every quantum tunneling event from the subatomic scale to cosmic phenomena occurs within a framework of natural error correction mechanisms that preserve information and maintain the coherent operation of physical laws across vast scales of space and time. Quantum error correction in natural systems operates through principles that were only recently discovered in the development of quantum computing technologies. These mechanisms ensure that crucial information about physical states and processes remains preserved even when individual quantum events introduce apparent errors or uncertainties. The universe appears to implement sophisticated error correction protocols that prevent the accumulation of quantum errors from destabilizing the large-scale structures and processes we observe. Consider how biological systems maintain genetic information, despite the constant bombardment of quantum tunneling events that could potentially corrupt DNA sequences. The double helix structure of DNA provides natural error correction through complementary base pairing, where quantum tunneling-induced errors in one strand can be detected and corrected using information stored in the complementary strand. Cellular repair mechanisms continuously scan DNA sequences for mismatched base pairs that might result from quantum tunneling events, correcting these errors before they can propagate through subsequent generations. The fidelity of DNA replication approaches the theoretical limits of error correction, achieving error rates below 1 mistake per billion copied nucleotides. This extraordinary accuracy requires multiple layers of quantum error correction, from the molecular recognition processes that ensure correct base pairing to the proofreading enzymes that detect and correct incorporation errors. Each layer exploits quantum mechanical properties while maintaining classical reliability through redundancy and error-checking protocols. Protein folding represents another example of biological quantum error correction operating at the molecular scale. The process of folding complex proteins into their functional three-dimensional structures involves navigating astronomically complex energy landscapes, where quantum tunneling enables transitions between different conformational states. Yet proteins fold reliably into their correct structures with remarkable consistency, suggesting that evolution has developed sophisticated error correction mechanisms that guide folding processes along productive pathways. Molecular chaperones serve as biological error correction systems that assist protein folding by preventing misfolding events and providing mechanisms for refolding proteins that have adopted incorrect conformations. These systems operate through quantum mechanical recognition processes that can distinguish between correct and incorrect protein structures, enabling error detection and correction at the molecular level. The operation of cellular metabolic networks demonstrates quantum error correction principles operating across entire biochemical systems. Metabolic pathways involve hundreds of enzymatic reactions, each subject to quantum tunneling effects and thermal fluctuations that could potentially disrupt cellular function. Yet cells maintain homeostatic regulation of their internal chemistry through feedback mechanisms that detect and correct deviations from optimal operating conditions. Enzyme regulation through allosteric mechanisms provides examples of quantum error correction operating through conformational changes in protein structures. These regulatory systems can detect when metabolic pathways are operating outside their optimal ranges and respond by modifying enzyme activities to restore proper biochemical balance. The detection and correction processes often involve quantum tunneling events in protein conformational changes that enable sensitive response to chemical signals. At larger scales, ecological systems demonstrate error correction principles that maintain stability despite fluctuations in individual population dynamics. Predator-prey relationships create feedback loops that prevent any single species from growing to levels that would destabilize the entire ecosystem. These regulatory mechanisms operate through information processing networks that span multiple trophic levels, creating distributed error correction systems that maintain ecological balance. The Earth's climate system exhibits error correction properties that have maintained relatively stable conditions suitable for life over geological timescales. Feedback mechanisms involving atmospheric composition, ocean circulation, and biological processes create regulatory systems that respond to perturbations by restoring climatic equilibrium. These planetary-scale error correction mechanisms operate through complex interactions between physical, chemical, and biological processes. Stellar evolution provides examples of error correction operating on cosmic scales through the self-regulating properties of stellar nuclear fusion. The temperature dependence of quantum tunneling-enhanced fusion rates creates negative feedback that stabilizes stellar cores against gravitational collapse or thermal runaway. When stellar cores become slightly hotter than equilibrium, fusion rates increase dramatically, generating additional pressure that causes expansion and cooling, automatically restoring thermal balance. The cosmic microwave background radiation reveals evidence of error correction mechanisms operating during the earliest epochs of universe evolution. The remarkable uniformity of this fossil radiation suggests that quantum fluctuations during cosmic inflation were subject to correction processes that prevented the development of large-scale inhomogeneities that could have disrupted galaxy formation and cosmic structure development. Quantum field theory itself exhibits error correction properties through renormalization procedures that eliminate infinities from physical calculations. these mathematical techniques represent more than computational conveniences. They reflect deep principles about how quantum systems maintain finite, well-defined properties despite the infinite possibilities inherent in quantum superposition states. The gauge symmetries that govern fundamental forces in particle physics provide natural error correction mechanisms that preserve conservation laws and maintain the consistency of physical interactions. These symmetries ensure that physical processes respect fundamental conservation principles, even when individual quantum events appear to violate classical conservation laws through virtual particle creation and annihilation processes. Spontaneous symmetry breaking in quantum field theory demonstrates how error correction can emerge naturally from quantum mechanical processes. When quantum systems spontaneously select particular vacuum states from among multiple possibilities, they create error correction mechanisms that maintain the stability of the chosen state against perturbations that might induce transitions to alternative configurations. The holographic principle suggests that quantum error correction might operate through information storage and processing occurring on the boundaries of space-time regions. From this perspective, the three-dimensional physics we observe might emerge from error-corrected information processing occurring in lower-dimensional holographic representations of physical reality. Black hole thermodynamics provides examples of quantum error correction operating under the most extreme physical conditions imaginable. The information paradox associated with black hole evaporation has led to proposals that quantum error correction mechanisms preserve information even when matter falls into black holes, enabling information recovery through Hawking radiation processes that maintain unitarity in quantum evolution. The ADS-CFT correspondence in string theory demonstrates explicit mathematical relationships between quantum error correction in holographic boundary theories and the emergence of space-time geometry in the bulk regions they describe. These correspondences suggest that space-time itself might emerge from error-corrected quantum information processing occurring in lower-dimensional quantum systems. Topological quantum error correction provides the most robust known methods for preserving quantum information against environmental decoherence. These techniques exploit the topological properties of quantum states to create error correction codes that remain stable against local perturbations, while maintaining the quantum correlations necessary for quantum computation and information storage. The development of fault-tolerant quantum computers requires implementing error correction protocols that can preserve quantum information indefinitely, despite the constant threat of decoherence from environmental interactions. These technologies provide practical tools for studying the limits and capabilities of quantum error correction in artificial systems designed to maintain quantum coherence under challenging conditions. Quantum error correction in artificial systems reveals deep connections between information theory, thermodynamics, and quantum mechanics. The energy costs associated with error correction operations appear to be governed by fundamental thermodynamic principles that relate information processing to entropy production and energy dissipation. The study of quantum error correction has revealed that information processing capabilities might represent the most fundamental currency of physical reality. From this perspective, matter and energy serve as substrates for information processing operations, with physical laws emerging from the requirements for stable, error-corrected information storage and manipulation. Decoherence theory provides detailed mathematical descriptions of how quantum systems lose coherence through interactions with environmental degrees of freedom. Yet, this loss of coherence doesn't necessarily represent genuine information loss, if error correction mechanisms can recover the lost information from correlations with the environment. The emergence of classical physics from quantum foundations can be understood as a large-scale error correction process, where macroscopic observables become effectively decoupled from microscopic quantum fluctuations. Classical determinism emerges not because quantum mechanics fails at large scales, but because error correction mechanisms suppress the propagation of quantum uncertainties to macroscopic levels. Biological evolution itself can be viewed as a cosmic-scale error correction process, where natural selection preserves beneficial genetic information while eliminating harmful mutations. The information processing capabilities of living systems continue to increase over evolutionary time, suggesting that the universe might be engaged in a long-term error correction project that generates ever more sophisticated information processing capabilities. The anthropic principle takes on new meaning when viewed through the lens of quantum error correction. The apparent fine-tuning of physical constants that enables complex information processing systems like life and consciousness might reflect the operation of cosmic error correction mechanisms that maintain the stability of information processing friendly physics. Consciousness itself might represent the universe's most sophisticated error correction system, capable of detecting and correcting inconsistencies in information processing that simpler physical systems cannot address. The subjective experience of consciousness could emerge from error correction operations that maintain the coherent integration of information across neural networks. As we contemplate these possibilities, we encounter the remarkable notion that reality might be engaged in a continuous process of self-correction and self-improvement, using quantum mechanical processes to explore possibilities while employing error correction mechanisms to preserve valuable information and maintain operational stability. Every quantum tunneling event becomes part of a vast cosmic computation that generates and maintains the complex structures we observe, from atoms and molecules to stars and galaxies to the intricate information processing systems we call life and consciousness. The universe emerges not as a collection of objects moving through space and time, but as an ongoing information processing operation that uses quantum mechanics to explore possibilities while employing error correction to maintain coherence and build complexity. We exist not merely as observers of this cosmic computation, but as active participants in the universe's ongoing project of understanding and improving itself through ever more sophisticated error correction mechanisms that preserve and extend the reach of information processing throughout space and time. Still here, friend? If your eyes are getting heavy, it's okay to let them close. Your mind remembers the way. But if you're still awake, there's another video waiting for you. I'll be here if you'd like a little more company. Either way, thank you for spending your night here. May your dreams be calm, your breath gentle, and your thoughts float softly like stardust. Sleep well among the stars.